Hello, this is SensorLab. I will introduce you to a high-precision multi-turn absolute position sensor optimized for robots. 24-bit high-resolution, multi-turn absolute, large hollow shaft, gear-type disc and magnetic disc, maximum 8 multi-slaves, BSSC communication interface. Introduction.
Hi, this is SensorLab. We will introduce you to a high-precision multi-turn absolute position sensor optimized for robots. This sensor is mounted on the output shaft of the reducer in an actuator of an industrial or collaborative robot to sense the final position. And this is suitable for safety detection and teaching the robot. As you can see, the Gearcoder is a magnetic sensor used in combination with gears. The Gearcoder can be used in combination with not only a gear but also magnetic scale. In this video, we recommend using it in combination with a gear. Some of you may look at this and say, I know that. That is a speed sensor. Right? This is a similar structure to what is often called a speed sensor. You can only use speed sensors to control the speed of induction motors, which are not precise. However, you can use this to detect accurate position. Although the sensing principle and mechanical structure of this and speed sensor are similar, their performance is completely different. We will prepare another video and compare and explain this. As you can see, the Gearcoder consists of gears, a PCB, and a strong permanent magnet, such as a neodymium magnet or samarium cobalt magnet attached to the back of the PCB. The magnetic flux from the permanent magnet flows through the PCB and into the gear. Magnetic flux flows through the protruding parts of the gear, but not through the recessed parts. By sensing magnetic flux density, the Gearcoder can sense the accurate position of one tooth period of a gear. Basically, the position can be calculated with the resolution divided by 2 to the 16th power, or 65,536, for one period of the gear teeth. For example, if it is a gear with one module, the interval between teeth is about 3.14 millimeters, so the Gearcoder can sense the position with a resolution of about 0.048 micrometers by dividing 3.14 millimeters by 65,536. Like this sensor, when there are 64 gear teeth per rotation, the Gearcoder can sense the position of one revolution with 22-bit resolution. You can calculate the resolution is 2 to the 22nd power by multiplying 2 to the 6th power by 2 to the 16th power. We will demonstrate how the Gearcoder senses position by rotating the scale. We will set the parameters of the Gearcoder. We will set it to single-turn 20-bit and multi-turn 8-bit. We will show you the position data sensed by the Gearcoder while rotating the scale by hand. The RS-422 based by SS protocol has been applied to transmit absolute position data, and RS-485 communication is also possible. The red clock hand is the absolute position angle at 360 degrees, and the green is the multi-rotation position, that is, the rotation count. We'll turn it by hand to put the current position near 0. Looking at the numbers, the single-turn position is 359.78 degrees and the multi-turn is 33 turns. We will rotate it slowly. The two clock hands rotate depending on the rotation. When the red clock hand rotates once, the green hand moves one step. It's hard to see it in one step, so you can see the numbers here. The number of turns, that is the rotation count, has increased by 1. When I turn it about 5 times again, you will see that the red clock hand turns quickly and the green hand moves slowly, increasing the multi-turn count by 5. Now, I will briefly explain the features of the Gearcoder. I will explain the principles of each feature by making other clips. When you watch this video, you might think, oh, this is what it's like. If you think it makes no sense or are curious about how it happens, please refer to the following videos or contact us. First, the gear-type structure makes it almost impossible to damage the magnetic scale by demagnetization or malfunction due to the magnetic scale being distorted by impact, which are disadvantages of magnetic sensors commonly used in robots. Second, the Gearcoder is a multi-turn absolute position sensor. By mounting the Gearcoder to the output shaft of your robot's reducer, you can see not only the absolute position of the reducer, but also how many turns it has made, so you can avoid kinks in the wiring. When the Gearcoder is turned off, it detects multiple turns and changes in the number of teeth using a battery at ultra-low power, and when turned on, it detects the accurate position and transmits position data. Typically, battery life is 10 to 20 years. Third, the hollow diameter and outer diameter can be freely designed. Other sensors have a few specifications for hollow diameter and outer diameter, so they cannot be designed as the user wants. You can change the gear module to 0.5, 1.0, 1.5. In particular, the number of gear teeth can be freely designed not only as a multiple of 2, binary, as 32 or 64, but also as an arbitrary number such as 29 or 31.
Freely design hollow disk size.
I will briefly explain how to freely design the scale outer diameter and hollow diameter of the Gearcoder. I will demonstrate position sensing with a single turn resolution of 20-bit, 25-bit, and 26-bit with one sensor using two scales with 64 and 32 teeth. This sensor is mounted on the output shaft of the reducer in an actuator of an industrial or collaborative robot to sense the final position. And this is suitable for safety detection and teaching the robot. Most hollow encoders have fixed hollow diameters and outer diameters, but the Gearcoder's disks can freely change size. The Gearcoder can be used in combination with not only a gear but also a magnetic scale. In this video, we recommend using it in combination with a gear. Because the scale of the Gearcoder is one track, it is easy to think of it as an incremental encoder, but the Gearcoder is a multi-turn absolute position encoder. For more information, please refer to the introduction video about the Gearcoder and the multi-turn function demonstration video in the description link below. While molds and magnetizing jigs are required to manufacture magnetic scales, a gear-type scale can be manufactured by cutting various shapes relatively quickly and inexpensively. While most magnetic encoder scales have a fixed number of magnet poles, the Gearcoder can freely determine the number of magnet poles or gear teeth regardless of resolution. Of the two gears on the right, the larger scale has 64 teeth, and the smaller scale has 32 teeth. As I mentioned, let's apply the fact that the number of gear teeth can be freely changed to design. The scale gear module is set to 1, and the desired outer diameter is 180 mm. Let's first calculate the diameter of the pitch circle of the gear. The radius of the pitch circle must be subtracted from the outer radius by the height of the tooth tip. Addendum. The tip height of the gear teeth is the same as the module, so it is 1, and the pitch diameter is 178 mm by subtracting 2 times 1 from 180. The root height of the gear teeth is 1.25 times that of the module, so it is 1.25 mm. If the thickness of the center below the gear teeth is set to 6.75 mm, the hollow diameter is 162 mm, which is the pitch diameter of 178-16. The calculated scale specifications are Module 1, outer diameter 180, hollow diameter 162 mm, and number of gear teeth 178. Since the resolution of the Gearcoder is not determined by a multiple of the number of gear teeth, you can set the desired single-turn resolution to 24-bit per revolution or 25-bit per revolution. For example, when the number of gear teeth is 10, the resolution can be set to 20-bit per revolution. Like this, you can calculate the number of teeth based on the diameter and hollow diameter of the scale you want. And you can set the resolution you want regardless of the number of teeth. For example, in a 6-axis robot, the size of each joint is different, so the scale specifications are different, but the position resolution can be unified at 24 bits per revolution. In this video, I will demonstrate position sensing with a single-turn resolution of 20 bits using a scale with 64 teeth, and position sensing with resolutions of 25, 20, and 26 bits using a scale with 32 teeth. Position sensing using a scale with 64 teeth was demonstrated in detail in another video, so please refer to it, and I will briefly show it here. I set the single-turn position resolution of the encoder with a scale of 64 teeth to 20 bits. When the scale rotates one revolution, single-turn position data increases or decreases by 1,048,576 counts, and multi-turn position data increases or decreases by 1. I will freely set the encoder's resolution with a scale of 32 teeth to 25, 20, or 26-bit per revolution. First, I set the encoder's single-turn resolution to 25 bits. Compared to the scale of 64 teeth, the number of teeth was reduced by half to 32, but the resolution was increased by 32 times or 5 bits. The current single-turn position is 358.08 degrees and 33,373,374 counts, and the multi-turn position is 8 counts. I will turn the scale to its current position near 0 degrees. The current position is 4 degrees, multi-turn 9 counts. Now, let's rotate the scale 1 revolution. When making one rotation, the current single-turn position increases by more than 30 million counts and then increases again from 0, and the current single-turn position is 1.42 degrees and 132,200 counts. Multi-turn increased by 1 to 10 counts. Here, you can see that the resolution per revolution is displayed as 33,554,432 counts. I'm going to rotate the scale 1 rotation in the opposite direction. The multi-turn count decreases by 1 and is 9, and the single-turn position is about 0 degrees, about 300,000 counts. If I repeatedly move the scale near 0 degrees, I can see that it repeatedly changes from the maximum resolution of over 33 million to about 0. I'm going to rotate the scale forward about 90 degrees. The current single-turn position is about 8 million counts, 1/4 of 25 bits. I'm going to rotate the scale forward about 180 degrees. The current single-turn position is about 16 million counts, half of 25 bits. Second, I changed the single-turn resolution to 20 bits while keeping the sensor and scale the same. I will turn the scale to its current position near 0 degrees. The current position is 2 degrees, multi-turn 10 counts. Now, let's rotate the scale 1 revolution. Multi-turn increased by 1 to 11 counts. When making one rotation, the current single-turn position increases by more than 1 million counts and then increases again from 0, and the current single-turn position is 1.24 degrees and 3,624 counts. Here, you can see that the resolution per revolution is displayed as 1,048,576 counts. Third, I changed the single-turn resolution to 26 bits while keeping the sensor and scale the same. There is no special effect in setting the single-turn resolution of an encoder with a scale of 36 teeth to 26 bits. In sensors using a scale with 32 teeth, there is actually little difference in performance between resolutions of 25 bits per revolution and 26 bits per revolution. In this clip, I am showing that the resolution can be freely changed regardless of the number of teeth. I will turn the scale to its current position near 0 degrees. The current position is 2 degrees, multi-turn 11 counts. Now, let's rotate the scale 1 revolution. When making one rotation, the current single-turn position increases by more than 67 million counts and then increases again from 0. And the current single-turn position is 359.8 degrees and 67,081,762 counts. Here, you can see that the resolution per revolution is displayed as 67,108,864 counts. The Gearcoder is an absolute position sensor that can be freely designed with a scale, has a position resolution of over 25 bits, and consumes little current, so the battery can be used for over 20 years without replacement. Optimized for robots, the hollow diameter can be enlarged, and data from multiple sensors can be received with one cable.
Multi-turn absolute encoder.
In this video, I will explain why the Gearcoder can be called a multi-turn absolute position sensor. So, what is a multi-turn absolute position sensor? The Gearcoder accurately recognizes the current position even if the robot arm moves while the main power is turned off. If the controller does not know the moving angle of the robot arm when the main power is turned off, the robot position must be returned to the origin every time it is turned off and on. And if the robot arm turns too far to one side, the cable may break. The multi-turn absolute position sensor uses low or no power during a power outage. It must detect how many turns the robot arm has rotated when it moves due to inertia or the user. When the power is turned on, it must accurately sense the rotation count and current angle and inform the controller of the position data. As a simple demonstration, I will first move the sensor with the main power turned off, then turn the power back on, and then show how to detect the number of revolutions and angle of movement. Before the main power is turned off, the number of revolutions is 32, and the current angle is 195.5 degrees. Now, I turn off the main power and quickly rotate the sensor disk. A communication error occurs on the master side, and the position data does not change. Let's turn the main power back on, reconnect with the receiving master, and read the position data. The rotation count was suddenly updated to 71 turns, and the current angle was 78.6 degrees. When the sensor rotates quickly with the power turned off, you can see that it has rotated 39 times in the forward direction and stopped at the current position of 78 degrees. You can see from the triangle mark on the disc that it is approximately 78 degrees. This way, the Gearcoder can detect the number of rotations and the current angle when the main power is turned off. I will explain in more detail a demonstration of multi-turn absolute position sensing under several conditions. I configured the test equipment with a rotating jig connected to the Gearcoder, a BISS data master, a laptop, a main power supply, and a switch that turns the main power on and off. The test sequence is as follows. First, when the main power is turned on, I read the current number of rotations and angle to the laptop through the receiving master. Second, I turned off the main power, and communication between the master and the sensor was lost. Third, with the main power turned off, I rotate the disk of the Gearcoder. Fourth, turn on the main power again and read the current number of rotations and angle. Check whether the number of rotations has been appropriately read when turned off. Let's start testing. The main power is on, and the Gearcoder LED is green. I will rotate the disk so that the current angle is close to 0. The current number of rotations is 0, and the current angle is 2.78 degrees. When I turn off the main power, the LED on the Gearcoder turns off, and a communication error occurs on the laptop connected to the receiving master. I will move the disk to a 90-degree position with the main power turned off. When I turn on the main power, the LED on the sensor lights up green. I will reconnect communication with the Gearcoder and the receiving master and read the position data. The current number of rotations is 0, and the angle has been updated to 95 degrees. I will turn off the main power once again, rotate the disk one turn, and move it to the 180-degree position. When I turn on the main power, the LED on the sensor lights up green. After reconnecting the sensor to the master, I will read the position data. The current number of rotations is 1, and the angle has been updated to 185.9 degrees. I will turn off the main power again, rotate the disk twice, and move it to the 270-degree position. I will turn on the main power, reconnect the sensor and master, and then read the position data. The current number of rotations is 3, and the angle has been updated to 275.6 degrees. This time, let's test in the opposite direction. Likewise, turn off the main power, and I will rotate the disk 3 times in the opposite direction and move it to near 0 degrees. When I turn on the main power, the LED on the sensor lights up green. After reconnecting the sensor and master communication, let's read the position data. The current number of rotations is 0, and the angle has been updated to 16.5 degrees. I can see that when the main power is turned off, and the disk is rotated in the forward and reverse directions, the Gearcoder can detect the number of rotations and the angle. This time, I will test the position sensing when the disk rotates quickly using the motor while the sensor power is turned off. In the actual test of position sensing during a power outage of the Gearcoder, rather than a demonstration, the power is turned on and off repeatedly when rotating at various speeds using a motor. By repeatedly turning the main power of the Gearcoder on and off, the position deviation of the reference sensor for comparison with the Gearcoder is measured to verify the current rotation count and angle sensing function. Let's spin the disk quickly with the main power turned on. The red needle indicates that the angle rotates rapidly, and the number of rotations displayed at the bottom increases. When the rotation stops, the number of turns is 32, and the angle is 195.5 degrees. I will turn off the main power and quickly spin the disk at the same speed. The needle does not move because communication is lost. Turn on the main power, reconnect the sensor and master, and then read the position data. The number of rotations is 71, and the current angle has been updated to 78.6 degrees. You can see that the disk rotated 38 times and 243.6 degrees when the power was turned off. I will test it this time by rotating the disk in the opposite direction. Likewise, we will turn off the main power and quickly spin the disk at the same speed. The needle does not move because communication is lost. I will turn on the main power and read the location data. The current number of turns is 25, and the angle is 264.4 degrees. You can see that the disk rotated 45 times and 174.2 degrees in the reverse direction when the power was turned off. So far, I have shown that Gearcoder can detect the number of turns and angle changes when the main power is turned off, and transmit absolute position information, including multi-turns after the main power is turned on. After listening to the explanation, you may think it was just turned on with batteries when the main power was turned off. Please watch the Gearcoder's battery consumption video if you think this way. I will only talk briefly here. The critical point is how low the current consumption can be to detect the position normally after the main power is turned off. The Gearcoder can be used without replacement for over 20 years when using a typical 3.6 volts battery. The Gearcoder current consumption is approximately 16.5 microamperes when operating on battery, which is 30% of that of other battery-type encoders. Compared to the main power operation, position changes can be sensed normally while consuming only 1.4% of current during a power outage.
How long can the battery last?
I will briefly summarize the results and explain in more detail. This is the result of measuring battery consumption during a power outage. The sensor uses capacitor power for approximately 4 hours and 30 minutes after the main power is off, consuming very little power from the battery. After consuming all the power charged in the capacitor, it operates as a battery, and the current consumption is about 16 microamperes. When using a typical servo battery, the battery life is more than 20 years. The Gearcoder is a battery-powered encoder that detects gear rotation and single-turn absolute position at ultra-low power during power outages. Since the demonstration lasts about 5 hours, I will explain while playing the demonstration video at high speed. After turning off the main power, let's test how much current the Gearcoder consumes. There is a rotating jig equipped with the Gearcoder, and a 2-channel power supply to supply 5 volts main power, and 3.3 volts battery power. Now, when the main power is supplied, the Gearcoder will operate. The main voltage and current are displayed on the left side of the power supply's monitoring window, and are currently 5 volts, 120 milliamperes. The battery power voltage is displayed on the right side of the power supply and is 3.3 volts. The battery current consumption was too low to be measured by the power supply, so I installed a current meter independently, and the current consumption was 2.83 microamperes. Currently, the Gearcoder operates using the main power and detects the accurate position. Let's read the sensor's position data using the master connected to the laptop. I rotate the sensor disk at about 600 revolutions per minute. Current consumption does not change even during rotation. Let's see what happens if I turn off the main power during operation. In fact, it is a similar test to turning off the power while the robot is operating. When the main power is turned off, the main current consumption of the power supply changes to 0. Communication is disconnected, as shown in the GUI on the left. Because the sensor entered an ultra-low power mode, stopping communication and accurate location detection. When the main power is off and the capacitor is charged, the sensor uses capacitor power in preference to battery power. Therefore, the battery current consumption does not change and is very low. The capacitor is fully charged in about 8 minutes after main power is supplied. To calculate the battery life of a battery-powered the Gearcoder, I will measure the operating time and current consumption using a capacitor. The video is very long, so I will play it quickly and explain it. You can see the demonstration and principle of detecting the rotation count with the main power turned off in another video. As the main power is off, the Gearcoder operates in ultra-low power mode. Initially, the Gearcoder uses the capacitor power, but when the voltage of the capacitor becomes lower than that of the battery, it operates using the battery power. In ultra-low power mode, the encoder counts the number of teeth moved to sense multi-turn and single-turn absolute positions, and doesn't perform the precise position calculation in the serial communication. The encoder can sense the absolute position of one tooth cycle by calculating the inverse tangent after turning on the main power. It only needs to count the number of teeth moved during a power outage. In ultra-low power mode, the encoder uses battery power, so the lower the current consumption, the longer the battery can run. I measure the current consumed when the battery is used in ultra-low power mode. When the capacitor voltage becomes lower than the battery voltage, the Gearcoder operates using the battery. The Gearcoder operating mode is the same as using a capacitor power, but battery current consumption increases. About 4 hours and 30 minutes have passed since I turned off the main power, and the battery current consumption is 2.8 microamperes. Looking at the ammeter, you can see that the battery current draw suddenly increases up to 16.5 microamperes. In other words, when the encoder operates using a battery, the current consumption is about 16.5 microamperes. Considering that the current consumption of Japan's battery-type multi-turn encoder for servo motors is 30-100 microamperes, this is a very low level of about 17-50%. After the main power was turned off, it took approximately 4 hours and 30 minutes for the capacitor to discharge, and the encoder to start using a battery. Let's calculate battery life. The first condition is to run the robot for 8 hours a day, and turn off the main power for 16 hours. Based on 1 day, main power operation, 8 hours, capacitor operation time, 4 hours, battery operation time, 12 hours. Battery current consumption when operating with main power or capacitor is 2.9 microamperes, and when with battery, current consumption is 16.5 microamperes. The total battery power consumption per day is 232 microampere-hour. You can use a typical battery with an electric capacity of 3000 mAh for 12,886 days or about 35 years. Under the same usage conditions, I will calculate the battery life when using an encoder without a capacitor. Based on 1 day, main power operation, 8 hours, capacitor operation time, 0 hour, battery operation time, 16 hours. Based on 1 day, battery current consumption when operating with main power is 2.9 microamperes, and when with battery, current consumption is 16.5 microamperes. The total battery power consumption per day is 287 microampere-hour. You can use the same battery with an electric capacity of 3000 mAh for 10,445 days or about 28 years. The second condition is when storing the robot or transporting it by ship for a long time. I will calculate how long it can operate in ultra-low power mode using the battery while the main power is continuously off. The encoder runs 24 hours a day using a battery. The total battery power consumption per day is 396 microampere-hour. Similarly, you can use the same battery for 7,575 days or about 20 years. In this video, when using the Gearcoder, we measured the battery current and calculated the battery's current consumption and lifespan according to operating conditions. If you use a typical battery, you can use the Gearcoder for over 20 years without replacing the battery.
Connecting 4 encoders on a robot with 1 cable.
This time, we will explain and demonstrate the function of simultaneously receiving multiple position data from multiple sensors with a single cable, which is essential for collaborative robots. First, we will briefly show you a video of receiving data from 4 sensors, and then we will explain in detail. As you can see, 4 sensors are arranged around 1 gear and connected in series. We receive 4 position data from 4 sensors over 1 cable. You can see 4 positions changing in the program for the master. As in collaborative robots, when a motor, sensor, and single-axis, servo, controller are in one actuator, one sensor is mounted on the motor shaft and the other is mounted on the output shaft of the reducer. A single-axis controller should receive position data from both sensors simultaneously. Fanuc, one of the world's largest robot companies, sells not only collaborative robots such as universal robots, but also industrial robot-based collaborative robots. A precision sensor is mounted on each output shaft of the reducer mounted on the robot's 6 joints, and is used for teaching mode and shock detection. The robot controller should receive the position data from the 6 sensors mounted on the joints. In summary, in a collaborative robot similar to the universal robots, the single-axis controller must receive position data from 2 sensors for each joint actuator, and in an industrial robot-based collaborative robot, the controller must receive position data from 6 sensors at joints. In service robots and wearable robots, hollow shaft sensors are mounted on large joints such as the waist and legs, and receiving position data from multiple sensors with a single cable has many advantages over receiving it through individual cables. We recommend using bi-SS communication to receive multiple position data at high speed. The protocol for receiving position data from most servo sensors or encoders is one-to-one communication. Considering CAN, EtherCAT or Profibus, do you think one-to-many communication is possible when using servo sensors? There are many differences between sensor communication protocols for high-speed feedback control and communication protocols for motion networks. When using sensors for monitoring, you can apply motion network-based communication such as EtherCAT or Profibus. But you cannot use it for servo control. While the motion network communication cycle is mainly hundreds of microsecond to several millisecond, sensor data communication for high-speed feedback control transmits only essential position data at high speed with a cycle of less than 30 to 100 microsecond. We explain the configuration of a demonstration device that receives position data from 4 sensors with one cable. It consists of 4 position sensors and MB5U, a bi-SS master kit that receives position data, a laptop to display position data, an oscilloscope to measure communication waveforms, and a power supply. We explain the principle of receiving position data by connecting 4 sensors in a series daisy chain. The clock signal requesting position data from MB5U, the bi-SS master kit, is transmitted simultaneously to 4 sensors. First, the slave 0 sensor located at the end of the master transmits position data to the slave 1 sensor right in front. The slave 1 sensor attaches the position data received from the slave 0 after its own position data, and transmits it to the slave 2 sensor right in front of it. The slave 2 sensor attaches the 2 position data received from the slave 1 after its own position data, and transmits it to the slave 3 sensor. The slave 3 sensor attaches 3 position data received from the slave 2 to its own position data, and transmits 4 position data to the master. In order from the sensor furthest from the master to the sensor closest, it is slave 0 to slave 4, and at the same time, it is channel 4 to channel 1. In this way, the master receives 4 position data synchronized to the clock signal. We will show the master and the notebook receiving position data. As you can see, 4 gearcoders are placed on one gear at about 90-degree intervals and connected in series. On the GUI, 4 positions are displayed on data channels 1 to 4, respectively. I will slowly rotate it by hand. The first data of each channel is the number of revolutions and the second data is the absolute position of a single rotation. For the 4 sensors, multi-turn data was set to 8 bits and single-turn data was set to 20 bits. Considering the position data length and communication time, the single-turn data was set to 20 bits, but it is possible to set it to 22 bits or more. When a single position data is incremented by 20 bits or 1,048,576 counts, the number of revolutions is increased by 1. We will show the changes in the positions of the 4 sensors in a picture similar to a clock. Since the positions of only 2 channels can be displayed at the same time, we will show you by switching the channels of the red and green hands. Since the origin is not set accurately, each sensor is not positioned at 90 or 180 degrees, but you can see that they rotate at the same speed and direction. You can see that the single-turn data for 4 channels gradually increases, and when it reaches 20 bits, the number of rotations increases by 1. Let's measure the time to transmit and receive position data from all 4 sensors. Oscilloscope channel 1 is the position signal sent from slave 3 sensor, and channel 2 is the clock signal sent from master. The speed of bi-SS communication is 5 MHz. The data length of one sensor is 36 bits, 8 bits for multi-turn, 20 bits for single-turn, 2 bits for errors and warnings, and 6 bits for CRC. There are 4 sensors, so a total data length is 144 bits. The data communication time is 28.8 microsecond, and including CDS and timeout, the total communication time is 31.3 microsecond. If the robot controller receives position data from 6 sensors, the total data length is 216 bits, the data communication time is 43.2 microsecond, and the total communication time is 45.7 microsecond. The following is an example of applying 6 sensors to the robot. The length of position data for one sensor is 40 bits, 12 bits for multi-turn, 20 bits for single-turn, 2 bits for errors and warnings, and 6 bits for CRC. There are 6 sensors, so a total of 240 bits. Data communication time is 48 microsecond and total communication time is 51.1 microsecond. In this way, in robot applications, although there is a difference depending on the number of sensors and the length of the position data from 6 sensors can be received serially using one cable in about 50 microsecond.
Large hollow shaft disc.
For gear-type discs, you can use regular gears. For this kit, I ordered a disc from the website Miss. The outer diameter of the disc is 80 mm and the hollow diameter is 48 mm. The Gearcoder disc can be manufactured with an inner diameter of 65 mm or more when the outer diameter is 80 mm, but the maximum inner diameter is 48 mm from the site. The module of the gear tie disc is 1, and the outer diameter is 80 mm, so the number of teeth is 80. It was made of carbon steel because it should be made of a magnetic material. It should not be manufactured with non-magnetic or weakly magnetic materials, such as aluminum. Below is a video from the side and top. You can see that the center of the disc is hollow, and the center hole is large. The gap between the disc and the Gearcoder is about 0.6 mm from the center of the Gearcoder, and the tolerance is about plus 0.1 mm to plus minus 0.2 mm. The smaller the tolerance, the more accurate the sensor is, so you can set the tolerance according to the characteristics of your product. You can see a silver magnet attached to the back of the sensor's PCB. As the convex and concave parts of the disc are positioned facing the Gearcoder with the magnet attached, the Gearcoder detects the strength and weakness of the magnetic flux density and senses the precise position. Next, I will show you the changes in the position data sensed by the Gearcoder by slowly moving the gear-type disc by hand. Please refer to the video about Gearcoder on the SensorLab channel for more details, such as the video of rotating the Gearcoder with a motor. On the left is a video viewed from the side, and on the right is the result of receiving and displaying location data. This Gearcoder is a multi-turn absolute position encoder, with a maximum multi-turn count of 8 bits and a single-turn resolution of 24 bits. The maximum multi-turn count can be set to 24 bits. The Gearcoder will be mounted on the reducer of each of the 6 joints of the robot. To shorten the communication time when receiving 6 position data through serial communication by connecting 6 Gearcoders with one cable, the maximum multi-turn count is set to 8 bits. Connecting multiple sensors with one cable may be unfamiliar to you. One cable connected to the robot's controller goes to the nearest 6th-axis Gearcoder, and another cable connected to the 6th-axis Gearcoder goes to the 5th-axis Gearcoder. If connected like this, one cable connected to the controller is enough to receive position data from 6 Gearcoders. For more detailed information, please refer to other videos on my channel. When I turn it on, the LED lights up and I read the position data. The current position is multi-turn 0 count and single-turn count 50,861. Since the single-turn resolution is 16,777,216 with 24 bits, the current count of 50,861 is 1.09 degrees. I rotated the disc past 90 degrees, 180 degrees, 270 degrees, and back to its original position of 360 degrees. The multi-turn has increased to 1 count and the current position is 3.45 degrees with 160,767 counts. If you look at the error and warning bit, it is 3. When a warning or error occurs, the output bit changes to 0, and the current value is 3, indicating that no error or warning has occurred. When I rotate the disc once again, when it approaches 360 degrees, the current position data is about 16,400,000 counts, which is about 353 degrees. When I rotate the disc a little more, as it passes 0 degrees, the multi-turn count increases to 2 and the current position suddenly decreases to 14,999 counts, becoming 2.47 degrees. If I move the disc in the opposite direction, the red needle indicating the current single-turn position moves in the opposite direction. As soon as it moves, the current single-turn position suddenly increases and then slowly decreases, and the multi-turn count decreases by 1 to 1. When the disc moves near 0 degrees, the single-turn current position decreases to a value close to 0, and when it exceeds 0, the count suddenly increases to about 16 million, reaching 357.8 degrees, and the multi-turn count changes from 1 to 0. If I move the disc slightly in the forward direction again and it passes the 0 position, the current position is 4,948 counts, 0.11 degrees, and the multi-turn count is 1. Next, I will move the disc at 90-degree intervals. When the disc moves by 90 degrees, the current position is approximately 420,000 counts, which is 1/4 of 16,777,216 counts. I show the change in single-turn position data as I move the disk 90 degrees, 180 degrees, 270 degrees, and 360 degrees. Each time the disk moves at 90-degree intervals, you can see that the position data increases by approximately 420,000 counts. When the disk moves about 360 degrees, the current position is about 24 bits or a value close to 0, and at the same time, the multi-turn changes by 1 depending on the direction of rotation. I will move the disk 180 degrees and 360 degrees in the opposite direction. As the disk moves at approximately 180-degree intervals, the current position decreases by approximately 840,000 counts. After passing position 0, the multi-turn decreases by 1 and becomes 0. Using a kit combining a large hollow disk and the Gearcoder, I demonstrate that the Gearcoder can sense the change in position when the disk rotates in both directions. What will the Gearcoder do if the disk tooth is broken or the magnet falls off while the robot is operating? When the Gearcoder operates normally, the error code is 3, as the error and warning bits are 1. I will lift the disk upward to simulate a broken tooth. The error code changes to 0, as the error and warning bits change to 0. The Gearcoder has built-in LEDs that display assembly status and error status. When an error occurs, you can see that among the LEDs built into Gearcoder, the red and yellow LEDs are turned on. When I move the disk downward, the red LED goes off, but the yellow LED stays on. The red LED indicates the current status, and the yellow LED indicates a disk assembly status in a latch state. As errors and warnings are latched, the Gearcoder continuously transmits error and warning bits to 0. To clear errors and warnings, you must reset the Gearcoder with a receiver such as a robot controller. If you subscribe and set the alarm, it will be convenient for you to watch the next video. Thank you for watching. SensorLab.